So we had started with Lassalle's invariance principle, the last lecture. So let us just quickly review this. So suppose omega is a compact set that is positively invariant, and suppose we have found a function v that is C1. C1 means differentiable and the derivative is continuous, such that this v satisfies v dot is less than or equal to 0 on this set omega. For this v, we will now find a set E such that v dot equal to 0 on this set E, and let M be the largest invariant set in E. Largest invariant set in E means it is invariant under the dynamics of this dynamical system, it is contained in E, and it is the largest such set. In other words, any other subset of E that satisfies these properties is also contained in M. If these conditions are satisfied, then every solution starting in omega approaches this set M as t tends to infinity. So, approach a set, we had seen this as a definition. So, what the Lassalle's invariance principle says that every solution starting in the set approaches M. In other words, for every initial condition the trajectory converges to M. What is the meaning of converging to a set? So, the distance of a point P from a set is defined as the distance of P to different points in M and the shortest such distance. So, this is a definition of distance of a point P from the set M. Now, as x evolves as a function of time, x of t is a point, and we look at the distance of x of t from the set M, and this distance decreases as t tends to infinity. That is a statement of the Lassalle's invariance principle. So, we had already encountered the situation of the pendulum example, in which the natural energy function to take did not satisfy strictly less than 0. So, let us do this example again. So, we this is what we call as friction. This is the situation of a pendulum. The original differential equation was of second order, which was equal to like this. This differential equation of second order we converted to a first order differential equation, two first order differential equations by introducing x2. So, x1 is the same as x and x2 is the derivative of x1, and these two first order differential equations we will now study the equilibrium point and the stability properties of the equilibrium point. So, for this dynamical system we will now see x2 and minus sine x1 minus bx2, this equal to 0 0. This gives us x1 equal to 0 and x2 equal to 0 as one of the equilibrium points. Yeah, of course, we could have x1 equal to pi also, that corresponds to the pendulum standing upwards, which we know is unstable. We can also obtain that as a conclusion by linearizing about that point and checking that the eigenvalues are, at least one of them is in the open right half plane. That we will keep as an exercise. What we will now check is whether this equilibrium point, whether 0, 0 is stable, asymptotically stable. This is what we will check now. For this purpose, we will take the Lyapunov function coming as the energy of the system. So, take V of x equal to 1 minus cos of x1. Why? Because this is the potential energy. So, what was our x1 variable? This is our pendulum when it undergoes a deviation of angle x1. Yeah. So, this is the angle. The time, how much does it get raised? The amount by which it gets raised is the potential energy accumulated into the system, and that turns out to be 1 minus cos x1, of course multiplied by the mass and the gravitational acceleration g. but we have considered a model where those parameters are not arising. This can be considered as normalization of the equations or as normalization of the mass to 1. This is only the potential energy. The other energy term is actually x2 square by 2. Let us check what happens if we take just x2 square. Yeah, so this is not really energy because this is not kinetic energy. The second term is not kinetic energy, but it's twice the kinetic energy. So let us check what happens to v dot of x. So this turns out to be del v by del x times f of x, and when we evaluate this, del v by del x is a row vector in which the first component here is the derivative of this with respect to x1, which is exactly sine of x1, and the derivative of this with respect to x2, that is 2x2 times f of x. What was f of x? The first component was x2, second component was minus sine x1 minus bx2, and when we multiply this product, this is like inner product, we get x2 sine x1 minus 2 times x2 sine x1 minus 2 b x2 square. So this is what we get as v dot of x. So is this quantity positive or negative? That is the next thing we will investigate. So we got v dot of x was equal to, this term is well behaved, but the other term is this is our x1, this is our x2. So one term of course doesn't change sign, it's always negative or equal to 0, but the other term x1 and x2, sine of x1 has the same sign as x1 close to x1 equal to 0, but x2 times this can change its sign depending on which quadrant it is, and hence for small values of x1 and x2, in other words close to the origin, we are not able to say that v dot of x is less than or equal to 0. This is not satisfied, close to 0 comma 0. This one can check oneself. In order to check oneself, one could first ignore this particular term. Why we can ignore this term? Because this is, to put b equal to 0 just means that we have a pendulum without friction, and for the pendulum without friction we know that the system is stable. By intuition we want to obtain that as a conclusion from the Lyapunov theorem of stability, and for that purpose this particular quantity certainly changes sign. Yeah, it will have different signs depending on x1 and x2 on each of these 4 quadrants, and hence this v dot does not satisfy less than or equal to 0. So this is not a valid Lyapunov function. Why? Because it is a Lyapunov candidate, it is positive definite, but it is not decreasing, it is not non-increasing around the origin. So let us go back to our Lyapunov function and make a small change here. We will now divide this by 2. This perhaps we have already verified once. So this now is indeed the kinetic energy. So by doing this, we do not get this 2 term here, and we remove this also here, because of which this term now cancels out, and we have v dot of x. Now it is indeed less than or equal to 0. Why? Because v dot of x was equal to minus b x2 square. So this at least proves that 0 comma 0 is stable. However, this had not helped us to prove that the origin is asymptotically stable, even though by intuition we know that the equilibrium point is in fact asymptotically stable, because we have friction which continuously dissipates off the energy. So how do we obtain that? This particular function Lyapunov candidate does not help us. However, we can use Lassalle's invariance principle for the same Lyapunov function. So construct the set E, set of all x, such that v dot of x was equal to 0. In other words, minus b x2 square equal to 0, it gives us set of all points where x2 is equal to 0. Yeah. So this x2 equal to 0 is nothing but the x1 axis. The x1 axis is a set of all points where rate of change of the Lyapunov function is equal to 0. So, this is our set E. Now, we want to look at the set M, which is subset of E, invariant under the dynamics of the system, and largest such set which satisfies that it is a subset of E and it is invariant under the dynamics of the system. So, how will we find the largest such set? We will look for what values of x1 and x2 are subset of E and are also invariant. When we try to do this, we will automatically get the set of all x1 x2 points that are invariant and contained in E, and hence it will be the largest such set. So, x2 equal to 0 is the requirement that the set M is contained in E. Now, we will put this in x1 dot equal to x2 and x2 dot equal to minus sine x1 minus b x2. When we put x2 equal to 0, we get x1 dot equal to 0. We also put x2. So, x of t is contained in set E, which means x2 of t is equal to 0, always is uniformly equal to 0, equivalently equal to 0, identically equal to 0. These are the different ways we interpret this symbol, this equation. So, if some particular value of x as a function of time is always equal to 0, it is like a constant function, which automatically means that x2 dot is also equal to 0 identically. So, when we put that x2 dot equal to 0, then we also get sine of x1 equal to 0. And this implies that sine of x1 equal to 0, which of course we know happens at either the vertically down position, which is x1 equal to 0, or the vertically up position, which is x1 equal to pi. Since we are interested about the stability properties of the position of the point 0 comma 0, we get this is of interest. Since we are interested at this point, we get that M is just the point 0 comma 0. Yeah, when we ask the question inside the set E, which are all those points which are invariant under the dynamics of F, that time we took the set E, which means we put the equation x2 equal to 0, and we studied invariance. By invariance, for invariance we put the fact that x2 is always equal to 0, which means x2 dot also equal to 0. When we substituted that back here, we got sine of x1 also equal to 0. This term was already 0, this term we now got equal to 0, because of which we obtained that sine of x1 equal to 0, and which means that this can happen at the point pi comma 0 also. The first component is equal to 0, that is one of interest, which is vertically down position. So, we have obtained that the set of all invariance points that satisfies the property that it is invariant and subset of E gives us only this point, and this is the largest such set. Yeah, any other set would not satisfy the equations. We looked for all the points that satisfy the equations and got this point. So, in other words, we have obtained that M is just the set, just the point 0 comma 0. So, what is the meaning? So, by Lassalle's invariance principle, x of t converges to the set M, which is just 0 comma 0. Yeah. So, this in other words proves that origin is not just stable, which we already concluded from the Lyapunov's theorem of stability, but we in fact got that the origin is asymptotically stable. So, this concludes proof of the statement that the origin is asymptotically stable by using what principle? Not by using Lyapunov's theorem of asymptotic stability, but by using Lassalle's invariance principle, which we used to conclude that the set M has just one point, the origin, and by Lassalle's invariance principle the trajectories x of t converge to M, and hence the origin is asymptotically stable. Now we will investigate whether the linearized system at this point is also asymptotically stable. So consider again x1 dot equal to x2 and x2 dot equal to minus sine x1 minus b x2. So x dot is equal to, this can be written as f1 of x and f2 of x as a vector. So what is linearization? Okay, we have already checked that the equilibrium point of interest is 0, 0. We have checked that this is an equilibrium point. Now what is this linearized system? It is this particular matrix evaluated at x equal to 0, 0. So let us find what this matrix is. The term that comes here is the derivative of f1 with respect to x1. So in f1, which is this equation, x1 does not come at all. In other words, the derivative of f1 with respect to x1 is 0. What is the derivative of f1 with respect to x2? That is the term that comes here, that is precisely equal to 1. Why? Because f1 of x is equal to x2. So derivative of f1 of x with respect to x2 is equal to 1. What is the derivative of f2 with respect to x1? So where all does x1 appear in this equation? It appears only here. In other words, derivative of minus sine x1 with respect to x1, that is minus cos x1. What is the derivative of this term with respect to x2? So x2 does not come here, it appears only here, and so we put minus b here. This, as expected, is a matrix, but it depends on x1 and x2. It depends only on x2 in this case. So we are now required to evaluate this at x equal to 0, at the origin. So which means that in the first two entries x1, x2 don't appear, it appears only here. When we put x1 equal to 0, we get minus 1, and of course b is greater than 0. So let us check how the eigenvalues of this matrix look. So upon checking, one can do the calculations and check that eigenvalues of A are in the open left half complex plane. Yeah, one can check that by using the fact that b is greater than 0, the eigenvalues of that particular matrix we wrote are both in the open left half plane, which means that the origin is asymptotically stable. And for a linearized system, if A is Hurwitz, if the origin of the linearized system has all eigenvalues in the open left half plane, then we know that the nonlinear system's equilibrium point is also asymptotically stable. However, that Lyapunov function could not help us with that. So can we find another Lyapunov function? After all, the Lyapunov theorem was only a sufficient condition for stability and asymptotic stability. Since we already know that the equilibrium point is asymptotically stable, can you find another Lyapunov function to show asymptotic stability? The energy function already helped us to prove stability, but we want to prove asymptotic stability. So we will consider finding a Lyapunov function for the linearized system. In other words, find p greater than 0 such that A transpose p plus pa is equal to q for q a negative definite matrix. This is a problem that we will solve now. Why? Because this particular Lyapunov function for the linearized system will also help as a Lyapunov function for the nonlinear system. So we can in fact choose for linear systems, because A is Hurwitz, for any q we will be able to find such a p. So take q equal to minus 1, 0, 0, minus 1. Yeah. In other words, this q will correspond to our v dot of x. So the corresponding v dot of x will turn out to be equal to minus x1 square minus x2 square. Why? Because v dot of x is nothing but x transpose qx. for linear systems. So when we put this particular q, we will get precisely this, and this we know is negative definite. It is strictly less than 0 for all x1 x2 except of course x1 equal to 0 and x2 equal to 0. So for this particular q, we will now look for a p such that find p such that A transpose P plus PA is equal to this q. Because that particular A is Hurwitz, the P that we will obtain from this equation will turn out to be positive definite matrix. This is the equation that we will solve now. So notice that A was equal to 0, 1 minus B. For the purpose of solving, we could take B equal to 1. This is the rate at which energy decreases due to friction, and this is required to be positive. So we have taken B equal to 1. What do we get by solving for P? We will assume P has these entries, yeah? P1, P2. P is a symmetric matrix, hence this entry is also equal to P2 and P3. So when we do A transpose P plus PA, that time we get this to be equal to this is A transpose. What is written here is A transpose times P1, P2, P2, P3 plus the same matrix P1, P2, P2, P3 times A, which was equal to 0, 1 minus 1, 1. So we will now evaluate this. This is equal to minus P2 minus P3. This is P1 plus P2, and here we have P2 plus P3. This is minus P2 minus P3 and P1 plus P2 and P2 plus P3. So now we will equate this to Q, and while doing that, so we can add these two matrices to get finally A transpose P plus PA is equal to minus 2 P2 P1 plus P2 minus P3. Here we get the same thing, P1 plus P2 minus P3, and here we get 2 P2 plus 2 P3. So since P was symmetric, we have got this particular matrix to be symmetric, and that is the reason that we should be choosing Q also to be symmetric, and we have chosen Q to be equal to, let us find values P1, P2, P3. A particular theorem we already saw claims that this system of equations is solvable. Yeah. So there are only 3 entries to 3 equations, 1, 2 and 3. Why? Because this entry equal to this is the same equation as this entry equal to 0. So let us put minus 2 P2 equal to minus 1, P1 plus P2 minus P3 is equal to 0, and finally 2 P2 plus 2 P3 equal to minus 1. So the first equation just tells that P2 is equal to 1 by 2, which when we substitute in the last equation, we get P3 was equal to minus 1 minus 2 P2. Yeah? So minus 2 times P2 is nothing but minus 1 again, which gives us P3 equal to, so we have taken A equal to 0, 1. Let us go back to this equation. We have got A equal to 0, 1 minus B, and we have put B equal to 1, and let us now take P equal to P1, P2, P2, P3. We have taken P to be symmetric, that is why we have taken the same entry here. So let us solve for A transpose P plus PA. This gives us, for A transpose, we will write 0 minus 1, 1 minus 1 times P1, P2, P2, P3 plus the same matrix P1, P2, P2 P3 times A, which is equal to 0 1 minus 1 minus 1. And when we solve this, so this when we do, we get minus P2 minus P3, P1 minus P2 and P2 minus P3 plus this particular matrix product. When we evaluate, we get minus P2 minus P3, P1 minus P2, P2 minus P3, and when we add these two matrices, we get minus 2 P2, P1 minus P2 minus P3, P1 minus P2 minus P3, and finally 2 P2 minus 2 P3. Yeah. So this matrix we have finally got is nothing but A transpose P plus P times A. Now we will equate this to Q. So we had already taken, so notice that this matrix is symmetric because we have taken P to be symmetric. This matrix has been obtained to be symmetric, and hence it is important that this matrix be equal to a Q which also should be assumed to be symmetric. So we have taken Q to be equal to minus 1 0 0 minus 1. So when we equate this matrix to Q, then we have, it appears like 4 equations. This entry equal to minus 1, this entry equal to 0, this entry equal to 0 is again the same equation. So it is not really 4 equations but 3. What is the last equation? This entry equal to minus 1. So these 4 equations now we will write here. So we have minus 2 P2 equal to minus 1, P1 minus P2 minus P3 equal to 0, and 2 P2 minus 2 P3 equal to minus 1. So the first equation gives us 1 by 2, which when we substitute into the last equation, we get 2 P3 is equal to 2 P2 plus 1, which was equal to 2. Yeah, when we put P2 equal to half, here we get 2. And these P1, P2 and P3, when we substitute into the second equation, we get P1 equal to P2 plus P3, which was equal to 2.5. Yeah. So what is our matrix P as a result of this? The matrix P was equal to P1, P2, P2, P3. So P1 has been obtained to be equal to 2.5, P2 was equal to 0.5, which is the same entry here, and finally P3, which was equal to 2. So the claim is that this matrix P that we have obtained is positive definite because A was Hurwitz and Q was negative definite. We can check this. So P greater than 0, how will we check this? One way to check that a matrix is positive definite is that all the principal minors, all the leading principal minors. So for a square symmetric matrix, this is a 1 by 1 minor. It is a principal minor because it is has the symmetric rows and columns taken to construct that submatrix, and only the leading ones. So we take only this now, and every such matrix we take and look at the determinant, and each of these determinants should be a positive number. That is a necessary and sufficient condition for this matrix P to be a positive definite matrix. So let us do that check for this. Here we have to take only 2 determinants. The first 1 by 1 determinant is nothing but 2.5. Yeah, P11, the first submatrix is equal to 2.5, that is greater than 0. What about the determinant of the whole matrix? The next leading principal minor is nothing but the whole matrix P. So the determinant of the whole matrix is 2 into 2.5 minus 0.5 square, which is equal to 5 minus 0.25, it is equal to 4.75, that is positive. So because both the first leading 1 by 1 minor and the second leading 2 by 2 minor are both positive determinant, this means that the matrix P is positive definite. So, if we had taken the Lyapunov function coming from this P for the linearized system, so what is the Lyapunov function? It is x transpose P x, in which P was, in which the matrix P was the one that we just now obtained. If we take this as our Lyapunov function, then the origin turns out to be asymptotically stable by Lyapunov's theorem of asymptotic stability, and the same Lyapunov function will also help us in proving asymptotic stability of the nonlinear system's equilibrium point, which happens to be the origin again. But if we had started with this Lyapunov function, then we would not have required Lassalle's invariance principle, because the Lyapunov function theorem itself would have stated that the equilibrium point is asymptotically stable. Unlike the energy function, unlike the physical energy that we had taken, which helped us to prove only stability by Lyapunov's theorem of stability. So, this completes Lyapunov analysis. We have seen some solved examples also. We can have another set of problems which we will use as exercises. We will now move on to the next topic, which is about periodic orbits. Why? Because periodic orbits are an important part in the context of building oscillators. So, before we move to that topic, there is one other slide that we had skipped. So, the Lassalle's invariance principle, which we saw in detail and also saw an example, is different from Lyapunov's theorem in two ways. The first way is, unlike the Lyapunov theorem, the Lassalle's invariance principle does not require the function V to be positive definite. Yeah, notice that we did not assume that V was positive definite. Second, the positive invariant set that we had constructed in the proof of the Lyapunov theorem, that set omega was constructed using the Lyapunov function V. Here we are assuming that we already have a positive invariant set. In fact, that is the reason that we are not assuming V as positive definite, because on a compact set omega, V always achieves its minimum, and we can subtract that minimum from the function V here, by which we can always obtain another function V that indeed is positive definite. Okay, we will also see an application of Lassalle's invariance principle. So, there are well known results that turn out to be a special case of the Lassalle's invariance principle. So, one of them is Barbashin-Krasovsky's theorems. What is the statement of the theorem? So, suppose x naught equal to f of x is a system in which x can have many components, x is an element of Rn, and suppose the origin is an equilibrium point. Suppose there exists a function V from a domain D to R, which is continuously differentiable, and suppose V is positive definite function. In other words, V of x is greater than 0 for all x except origin x equal to 0, and also V satisfies that it is less than or equal to 0 on the domain D. Construct the set M that is made up of all the points where V dot is equal to 0. Suppose this particular M has the property that the only solution that can remain inside M is xt identically equal to 0, then the origin is asymptotically stable. Notice that this is precisely the situation that had happened for the pendulum example with friction. So, the Barbashin-Krasovsky's theorem is a more general statement to this effect. What can we say about global asymptotic stability of that equilibrium point we just now claimed to be asymptotically stable? If V is radially unbounded, further in addition to the above assumptions, if V is also radially unbounded, then the origin is in fact globally asymptotically stable. So, this particular theorem we already saw for the case of a pendulum as far as asymptotic stability is concerned. Of course, the pendulum example, it is not globally asymptotically stable simply because there are other equilibrium points. However, the Barbashin-Krasovsky's theorem says that if V were radially unbounded, then the origin is in fact globally asymptotically stable. One can check that the Lyapunov function V we had used for the case of the pendulum example with friction, that is not going to be radially unbounded. Otherwise, the origin there would have been globally asymptotically stable according to this theorem.